Okay, thank you so much. So today I'm going to be presenting on the importance of geoscience in CCS from my perspective inside SLB's carbon storage team. So the agenda today, I'll be talking through what CCS is. I'll talk about CCS, the global status, what's going on worldwide in different projects. I'll talk about what we do within SLB in CCS. And I'll discuss a little bit about the role of geoscientists. So why it's so important that we have qualified geoscientists understanding what's going on in the subsurface for the carbon storage. I'll then touch on some case studies that we've worked on and end on the success factors, so what is required for a successful project, and hopefully a good Q&A discussion at the end. So what is CCS? CCS stands for carbon capture and storage. It's the removal and storage of carbon dioxide from the atmosphere into the subsurface. Usually capture occurs at a point source, such as a power station. The CO2 is captured and then it may be purified, compressed, and then transported to a location where it can be stored deep underground. Underground storage comes in many forms. The main form for most projects is in deep saline aquifers. These are porous strata which are saturated with brine or saline water. We also have storage possible in depleted fields, fields that have been in production for hydrocarbons. And then there's some unconventional CCS, for example, in basalt formations or in unminable coal seams, because CO2 absorbs onto the coal. So this is the CCS value chain. It all starts with the capture. This can be from a variety of industries, such as chemicals, cement, hydrogen production, power generation, and it can also be removal by DAC. This is direct air capture. So this is actually carbon negative, so removing CO2 from the air. It's fairly inefficient compared to capturing CO2 from a high concentration flue gas that you would get in industry. There are also some new developments being made, for example, looking at taking CO2 actually out of seawater and storing it that way to remove CO2 from the atmosphere. So the CO2 is then purified, it's conditioned, it's usually compressed, and then it's transported. And there's a variety of options for transport. Often projects use a combination of these, especially when they're getting from multiple sources to a single hub. So we could be using CO2 pipelines onshore or offshore. We might be using shipping carriers for CO2 to take it to an offshore terminal. For a smaller scale onshore project or to get to a terminal, we might be using trucks or rail as well. Then in terms of injection for commercial scale projects, currently either depleted fields or saline aquifers. As I mentioned, there's also less conventional or smaller scale or pilot projects that are looking at other storage options such as basalt or coal. Now, sometimes you'll see CCUS. In this case, the U is standing for utilization. Utilization is basically when the CO2 is being recycled. For example, the CO2 will be captured, but then it might be used to make your fizzy drinks, in your beer, or in your food or chemicals, or to make building materials such as concrete. We also use CO2 for enhanced oil recovery, where we actually inject the CO2 and flush out the remaining oil from a depleting field. So how does the CO2 stay in the subsurface? There's four main trapping mechanisms. The first and the most important is residual or capillary trapping. In the early phase of a project, this accounts for 95% of the trapped CO2 in the reservoir on average. This is when we inject CO2, it displaces the brine, and it's immobilized due to the effects of relative permeability and capillary pressure. Now, Structural or stratigraphic trapping. If you're in oil and gas, this is the most common form of trapping. Due to the buoyancy forces, CO2 will actually be trapped by a four-way closure anticline or stratigraphic or structural feature. Now, we also have, on a slightly longer scale, solubility trapping. This is on scales of 10 to hundreds of years when we inject CO2. Usually we're injecting CO2 as a supercritical, high purity state. So it's a supercritical, which means it's more like, acts like a liquid than a gas. So it's more stable. And the CO2 can actually, over longer periods, actually dissolve into the water, into the brine in formation. Now, there are projects that dissolve CO2 into water and then inject essentially carbonated water at high pressure into subsurface. This is used, for example, in Carbfix, and it's being also investigated at other locations to combine with geothermal, because you have the produced brine, you have a volume of water that you then re-inject, so you can dissolve the CO2 in that. And that takes us on to the mineral trapping. This is when CO2 actually interacts with the reservoir rock and precipitates minerals like carbonate minerals, and it's stored permanently as part of the rock. Now, Carbfix comes to mind. This is a project in Iceland where they are relying on mineral trapping. And why it's successful there is because the CO2 is injected, dissolved in the water, and then it reacts with the minerals in the basalts. So that's the method that they use in Carbfix. However, this is a more low volume method, because if you're dissolving CO2 in water, for every ton of CO2, you're going to need about 30 tons of water. So there's many places where you wouldn't be doing this due to lack of water, and also due to the volume you actually have to inject. So I always get questions on trapping. Do we need a structural trap for CO2 storage? And the answer is no. You don't need a structural trap. You just need a top seal. Now, there are advantages and disadvantages of having a structural trap. The advantages are you have a more predictable plume geometry, because the CO2 will only go as far as the spill points in the structure. And you will know where that CO2 is going to be for monitoring. So you know where to set up your MMV. That's measurement, monitoring, and verification, to ensure the CO2 is essentially where you put it. And often these structures are well characterized. They may have been depleted. They may be depleted oil and gas reservoirs, or they may have been investigated during oil and gas exploration as well. In general, you'll see in this picture, if we are injecting in one of these traps, we're injecting off the crest to avoid the pressure buildup as the buoyancy forces move the CO2 up to the top of the crest. If we inject in the crest, you're more likely to get some sort of change in stress of the reservoir, and actually potential to cause fractures in your caprock. So this takes us on to the advantages of the non-structural trapping. You can see two examples here. Here the dip is exaggerated. We only tend to inject if we have dip of less than 2 or 3 degrees, but we don't need a structural closure. We can inject in the basins where we have essentially flat strata or slightly dipping strata. The advantages of this is we don't have the issue with the pressure buildup at the top of the structure. We also have an unrestricted capacity. So essentially, we, instead of having an aerial extent of our structure, anywhere in the basin where we have the formation deep enough, good enough quality, and we have the seal, we can start injecting CO2. And we don't have a closed boundary. We have open boundary conditions. It also avoids some risks, such as faulting, that you often find associated with structures and structural traps. And we're less likely to need to remediate wells. Wells are one of the highest risks of a CO2 project for the leakage. And often in structures that are either depleted or previously explored, we'll have wells that penetrate the storage formation, which aren't designed to be in contact with CO2. And this causes a leakage risk, and you have to go in, you have to verify how these wells have been abandoned, and often re-enter the well and potentially plug it with CO2 resistant cement and remediate the wells securely. So often when you're in a large basin, you have the flexibility actually to avoid any wells that might be there already. So that brings us on to containment risks. So the biggest risks can be mitigated actually by injecting at a critical depth. So I talked about injecting CO2 in a supercritical state. This means we need to be at a high enough pressure and temperature to make sure that that CO2 doesn't transition into a gaseous phase. And the critical depth is around 3,000 feet. You'll see it around 800 to 1,000 meters, depending on the temperature gradient and the pressure gradient of individual geological formations. So we also consider the seismicity. So we don't want to be in an area where we have a lot of existing earthquakes or we're on an active fault zone. We also don't want to be injecting in a place where we're going to actually induce seismicity and cause small earthquakes due to the CO2 injection. Faults, as I mentioned, we try to avoid. When they're unavoidable, we need to ensure that they are fully sealing. We need to ensure that they're not going to be reactivated during injection. So we model the stress that will be applied to the fault during injection to ensure that this won't cause a pathway of leakage. As I mentioned, legacy wells will need to be abandoned correctly if there are legacy wells in the region. And it's not just the area where the CO2 plume goes that we're concerned about, it's also where the pressure plume goes, which is essentially the increase in pressure in the surrounding area due to the CO2 injection, because this can actually force brine up a legacy well from a deeper formation, potentially into a shallow formation. And cause contamination potentially of a drinking water aquifer. We also want to avoid impacting any subsurface operations, whether that's oil and gas production or storage or mining as well. Fractures, this is an important issue that we have to avoid. Fractures in the cap rock. It's more common if we're injecting into a carbonate or certain stratigraphies, but we need to model geomechanically the stress regime to ensure that the pressure buildup is not going to induce any fractures into our cap rock. We also consider the dip of the formation. CO2, as I mentioned, will move buoyantly up dip. So if we have an outcrop, 20 kilometers away and we have high dip, that can be a risk of CO2 moving quickly to the surface. We also need to consider what's on the surface. We tend to avoid areas that are highly populated. Obviously, we avoid that issue if we go offshore. That makes the project more expensive as well. We need to also consider the pore space rights in different legislations and the land ownership. USDW, sorry, this is US terminology. This is the underground source of drinking water, essentially a drinking water aquifer. And a lot of the focus around the environmental protection for CCS project is ensuring that there's no contamination of any source of drinking water in the subsurface. Now, this is an example from a project. This is looking actually at the containment risks that could be possible. So it was an analysis done for a project in Illinois. They were looking at potential leakage through wells. So are there any wells in the AOR? If there's no legacy wells, then there's no risk. They're looking also at the CO2 leakage to a shallower formation via the cap rock. So to avoid this, ensuring that your injection pressure, that your injection rate is low enough to keep the bottom hole pressure below 90% of the fracture gradient. That's the EPA rule for CARB, which is in California. It's actually, you have to keep to less than 80% of the fracture gradient, essentially ensuring the stress state of the cap rock is far away from the failure envelope. Additionally, considering the leakage through any faults, usually we have 3D seismic. It's required in many places to have 3D seismic to evaluate an area before we inject. In this project, no faults were initially picked on the 3D seismic. However, due to induced microseismic events that led to the interpretation of some faults near the basement. However, these events were less than magnitude 1.16, and the faults didn't penetrate through the cap rock. So that was considered a negligible risk. Another risk is CO2 leakage laterally to the outcrop. Due to the conditions, the CO2 migrated very slowly, and there was no outcrop of the formation, with the seal being regionally continuous for hundreds of kilometers. And finally, leakage through the project wells. Essentially, we need to be very careful when we construct the project wells, because these will be next to the highest concentration of CO2. They need to be designed as per regulation, and also ensuring we're using the right materials, such as for tubing, we want to use very high grade like chrome 25. And for the cement, we want to use something that's CO2 resistant as well, and confirm this by measurements as well, such as the isolation scanner to ensure well integrity. So let me move on to the global status. So why do we need carbon storage? So there's, in 2024, there were 37 gigatons of CO2 emissions, and out of that, only 51 megatons was captured. So this is 0.1% of all emissions. So we believe that around actually 60% of these emissions are addressable by CCS. But there's some hurdles to accelerate the ramp up of CCS. Although it's been around for a couple of decades, the project track record is small. There aren't many operating commercial projects. I can probably count them on two hands for permanent commercial sequestration of CO2. Also, the finance industry is immature in terms of tax credits, in terms of emissions trading schemes. It's still developing, and the confidence isn't necessarily there to develop projects for 30 years into the future. Also, there's an immaturity in the offtake agreements. It can be very complex between the different project partners, because you have the emitters, you have the transport, you have the storage. Then you've got to have offtake agreements between each party to say, oh, if the CO2 emissions cease, we stop getting the credits. But what if the storage has an issue and we can't store the emissions that we promised to take? So the offtake agreements get very, very complicated, also in terms of who is going to receive the tax credits. Will it be the emitter? Will it be the storage? So this is being developed, and is making progress in many of the big projects, especially the ones that are more of a hub model. We also have, we're improving actually the regulatory framework. So regulatory framework, it's different around the world. It's very well developed in the US, in Europe, in many European countries, it's being written into law. So we really see that the regulatory framework is improving. I would say in some places we don't have enough, and in some places it's too stringent. So there's definitely developments, and the more pilot projects that lead to commercial projects, they will help guide the framework. Also, public acceptance. This is a big issue on the storage, but also on the transport side. Building pipelines or moving CO2 can be fairly complicated in terms of gaining public acceptance and proving that we can do this in a safe manner. So sorry, this map is from 2023. I need to update, but in general, the trend is very similar as to where some of these major projects are. So in 2023, there were 41 facilities in operation. Now, this included pilot projects, and I expect, given all these blue operational dots in the US, this is also including EOR, so enhanced oil recovery as well. In terms of the major projects for permanent sequestration, we've got a couple in Canada. We've got Quest and Aquastore in Canada. In the US, we have one commercial project in the Illinois Basin, which has paused. Down in Brazil, projects are developing. This offshore, this is Petrobras, this is EOR. We have Snøhvit and Sleipner in the Norwegian, off the Norwegian coast. We had in Sala, this was a project in carbonates actually in Algeria that was suspended. All the projects in Europe, these are developing or pilot projects. Where else are they injecting? Gorgon down in Australia, they're injecting at a commercial scale there, and some also in China as well. So there's not a huge number where we're actually injecting, but there's a lot of projects in the pipeline, gaining permitting, doing geological evaluations, doing injection tests. So I think in the next 5 years, we'll have many, many more projects that are actually injecting CO2. And as you can see, the trend is increasing rapidly. We have a 57% year-on-year increase in terms of the capture capacity under construction, but obviously we need to match this with the ability to store as well. So it's balancing the storage with the capture as well. So in terms of policy, I mentioned some locations, some countries are very well developed in policy, where some have fairly weak to no policy at all. Leading the way is Western Europe and also the US and Canada as well. Australia, parts of Asia are pretty strong as well, but then you can see there are plenty of countries with absolutely no policy support for CCS. And in terms of different funding mechanisms, in the US, you have the 45Q. This is a tax credit that you can get up to $85 per ton of CO2 that you're storing. In the UK, sorry, the government, I have a slide coming up, but the government are funding a number of projects. And also we have the ETS, the emissions trading scheme as well. But this is it's more variable compared to the what's going on in the US now. So given we're in the UK, I thought I'd talk a little bit about what's going on here. So the UK government has been supporting the delivery of 4 CCS clusters aimed to capture between 20 and 30 million tonnes per year of CO2 by 2035. So they have announced in October last year 21.7 billion pounds of funding over the next 25 years. And this is to support initially the Teesside and the Merseyside clusters. And you can see in the picture on the right, these are the clusters of emitters onshore. And you can see on the left, these are the storage license blocks offshore. And you can go to the NSTA, the North Sea Transition Authority website, to get a deeper dive into who actually is the owner of these different license blocks. I put a few key names there on the slide. So the Track 1 projects, these are the Northern Endurance Partnership and HyNet. So Northern Endurance Partnership focuses largely on the Teesside emissions. There'll be a 145-kilometre pipeline that joins the emissions from onshore to saline aquifer storage in the Bunter sandstones in the North Sea, in the endurance structure there. There is also plans to, in future, connect this to the Humberside region and also for potential additional stores. The other Track 1 project being funded by the government is HyNet. This is using infrastructure from the Douglas platform and will be injecting into the depleted Hamilton gas fields. It's called HyNet because they're developing actually hydrogen production with CCS on Wales, as well as decarbonising industry in North Wales and along the coast there. The Track 2 projects, these were chosen for potential additional funding a few years down the line. These are the Acorn project up in Scotland. This is called the Scottish Cluster, so it's connecting the largest emission sources in Scotland to the North Sea, where they have a couple of stores. It's the Captain Sandstone Aquifer, the Goldeneye depleted field, and then extension into East May as well. Also, Track 2 is the Viking project. This is offshore of the offshore Grimsby. And this is looking at storage into the Viking area of the North Sea. Interestingly, there's additional projects being developed independently from the Track 1 and Track 2 by multiple companies, multiple operators. Perenco has 3 license blocks. They have the Orion project, which would be connected to the Humber region, and also Poseidon as well. Now, Poseidon is one of the biggest projects you might have seen, or biggest capacity storage fields in the region. You can actually watch a really nice video online if you go on the Perenco website. They've just completed a high volume injectivity test, the first of its kind in UK waters. They injected a few tens of thousands of tons of CO2 into one of the depleted fields in their license block, and they're planning to scale up by 2029. So that was really exciting because it was the first real CO2 injection in UK waters. Additional licenses are held by EnQuest, Spirit, Esso and Shell, and also Neptune, with the hope to connect that one to the Dutch Aramis project. Okay, so let me talk a little bit about what we do in SLB, in carbon capture and storage. So in terms of storage, we have over 100 years of global subsurface knowledge, largely in oilfield services. And we've been applying that to CCS for over 2 decades. We're involved in over 150 CCUS projects worldwide, with the scope all the way from feasibility through evaluation, through licensing, through FID, into operations in MMV, and through post-injection and closure. So we are involved in all the life cycle of CCS projects. So where do we work on these projects, onshore and offshore, both in saline aquifers and depleted fields, for EOR and also permanent geological storage? And industries we're working with are chemicals, oil and gas processing, cement, power, steel, oxygen, and BECCS as well, bioenergy with CCS. And you can see it largely matches the map that I showed previously of where the projects are. We've got projects in the US, is a very large chunk of our projects, but we also have up and coming projects in Brazil. We have operational projects in Australia, in Europe, developing ones in the Middle East and Asia as well. As well as storage, we're actually involved in the capture side of things as well, with SLB Capturi. We currently have multiple sites where we have an operational capture plants, and these are in Denmark, in Norway, and we recently were commissioned for capture of 800,000 tons per year in a project in the US. So this is for post-combustion capture using amines, and we have it at multiple different scales. It's a modular solution, so it can be applied from anywhere from tens of thousands of tons to up to 1 million tons per year. Of course, we're also operating in the usual storage side of things with the geoscience and engineering through our technology portfolio and also through the execution capabilities as well. So let me talk about the role of us geoscientists in CCS. So this is the project life cycle, all the way from screening to closure and post-closure. So within screening, this is where we're doing our regional site evaluations. We're choosing the best site for the storage. We then move into a more detailed site selection and evaluation. This is when we do site-specific modeling, maybe some early simulations, and we start providing input for permitting. We also moved to the design and development. Although a lot of this is on the surface, we need to use our geological knowledge to understand exactly where we need to have our CCS hub, where we have the best subsurface properties for drilling our wells and setting up our MMV plan. We also, as geoscientists, advise the construction, especially the drilling of the injection and monitoring wells and setting up our MMV. This, as I mentioned, MMV is measurement, monitoring and verification. This can cover a wide range of technologies from 4D seismic, repeated cross-well seismic, SDAS, so acoustic sensing, using fibers. We also use tracers where we can inject tracers with the CO2, use soil probes, use different sampling at different depths, and also pressure monitoring and other technologies as well. That's all included in the monitoring to understand where that CO2 is ending up. Is it staying where we put it? And then closure and post-closure. So when we finish injecting, we don't just leave a site and say, that's it, we're leaving. We have to be very careful to ensure we are continuously monitoring that site, because just because we've stopped injection doesn't mean that the CO2 has stopped moving in the subsurface. So depending on the legislation, we continue to monitor the site, model the CO2 plume until we can fully close the site or pass liability over to the state. And in some jurisdictions that may be 20 years, in other it may be maybe 50 years. So that's of course a very important step. So as a geologist, what are we most focused on in terms of the storage site appraisal? We're looking at capacity, injectivity and containment. So capacity is how much CO2 can be stored. We're looking at what pore space do we have access to, and what's the efficiency at which we can fill that pore space with CO2. In terms of injectivity, we're looking at how much CO2 we can inject per well. For example, can we inject 1 million tons per year, or can we only inject 10,000 tons per year? And that will determine how we're going to set up our field development plan, how many wells we're going to need, what the well spacing is going to look like, so we can optimize injection performance and long-term well integrity. Containment, of course, is the most important. What are the risks of leakage of that CO2 out of formation? And what monitoring technologies do we need to ensure we prove the containment? So I won't spend long on this slide. This is the process diagram of what we do in terms of data collection, modeling, iterative models, collecting data, acquiring new data via drilling wells, seismic, feeding that back into our models, running our flow simulations, our coupled simulations with geomechanics as well, and then moving on to our field injection plan, looking at our risk assessments, our MMV, our economics, and finally deciding when we get to FID if we're going to move forward with the project or not, based on all of our models and our evaluations. And this is a zoom in on the performance assessment workflow. A lot of this will maybe be familiar to geoscientists. So the data we're starting with, what do we have? It's very dependent on the project. Sometimes if it's a saline aquifer, we don't have any data at all. If it's a depleted field, we might have a full history matched model. So we have a variety of data that we're starting with. We're feeding this into our analysis, our petrophysics, our static modeling, our structural framework, our simulations, and looking at our coupled flow with our geomechanical stress models. And then we're outputting the capacity, injectivity, containment. We can model surface heave. That's actually when you inject the CO2 and it causes actually the land to change height, essentially. This can be measured via satellite imagery and also be predicted via our modeling. We can try and predict microseismicity if we're going to induce any significant events, and where will they be and the magnitude. And of course, flow assurance is very important. We need to ensure that the CO2 travels in a streamlined way from the pipeline into the well, down the well, and into the formation. And that has to be carefully modeled so we're at the correct pressure and temperatures in each of those steps. So I'm going to talk a little bit about a pilot project we were involved with. This was in the Illinois Basin. It was the first commercial scale dedicated storage in the US. It began as a Department of Energy funded project before being passed over to ADM company, who developed it as a commercial project. So this was injecting into a saline reservoir in Illinois. It was a proof of concept. It's been largely published. All this data is public. They publish best practices, knowledge sharing, and have visits from a lot of countries around the world. So back in 2014, they reached their initial goal of injecting 1 million tons of CO2 over a 3-year period into a 55-foot interval of the Mount Simon sandstone. The initial project, the IBDP project, formally closed in 2021. In total, it cost $91 million. And it was further developed, as I mentioned, to become a commercial scale project. So this is the type of analysis that would have been done prior to the injection of CO2. So first is looking at geological maps, geological cross-sections to understand the regional geology of the area. From this, we can have an idea of at what depths we're going to get our injection zones, at what depths we potentially have our sealing zones. In this case, the injection zones were focusing on high porosity sands, like this basalt Cambrian sand, the Mount Simon. And the seals were looking at the thicker sections of impermeable shales. When they drilled the stratigraphic test well, this is when we take all our wireline measurements, all our logs for petrophysics, also cores to analyze in the lab as well. They identified that we actually had 3 seals, which is great. If you have 1 seal, that's good, but often regulators like to see a secondary seal in case of leakage above the first seal. And here we even have a tertiary seal as well. And we have a nice deep formation where we're injecting. The Mount Simons, it's around 2 kilometer depth, but still has very good porosity and permeability based on the petrophysics and based on the lab measurements from the core. So detailed modeling was done. This was building up our 3D geological models prior to injection, and then rerunning during injection to try and match what we expected the CO2 plume was actually doing during injection. You can see here we actually have 2 injection wells. They injected in one for, I think, 2 years before moving to a second well, where they injected in a slightly shallower, still the Mount Simon, but a shallower zone. This was because the initial injection actually induced seismicity because it was fairly close to the crystalline basement. there were some small low magnitude seismic events, which was why for the second injection period, they actually moved up. You can see actually during injection, and this is pretty common for CCS projects, injectivity, which is the amount of CO2 you're injecting per year, falls over time. This is due to a number of factors, such as interaction of CO2 with the reservoir fluid, with the rock, a change in the temperature, a change in the pressure, which can increase CO2 viscosity and actually result in some sort of salt precipitation or rock contraction as well. Now, there are workovers that have been performed in some projects. It wasn't done here, to actually go and flush out the reservoir that's fairly close to the injection well to actually increase the injectivity again. As I mentioned, the microseismic fault interpretation. This is especially interesting for the geophysicists. There is often 3D that's shot across a region where we're going to inject CO2, the baseline 3D, and then after a number of years of injection, this may be shot again. And the change in the seismic can tell us actually where that CO2 is due to the response of the seismic from any CO2 injected. Now, this was the initial baseline survey. Originally, no faults were actually picked for the Mount Simon zone. However, after these microseismic events were detected and mapped, you can see that multiple faults were actually picked that went from the basement through the Mount Simon formation. The Eau Claire is the seal, that's this brown up here, and you can see that because none of the faults are penetrating all the way through the seal, it's unlikely that these would cause any impact in terms of leakage, but obviously any microseismic event is a concern, especially when you're injecting onshore and especially for public perception as well. So because they were monitoring, they had two monitoring wells, one for each injection well. This is the CCS 1 well and the monitoring well 1 that I'm showing here. And we're using a pulse neutron log to actually estimate the concentration of CO2 throughout the formation. You can see in this is CCS 1 well, as the injection is progressing and then pauses, we have a pretty consistent concentration of CO2. Once injection ceases, CO2 is actually concentration of reducing around the injection well. And you can see the response as well in the monitoring well. You can see the response is coming in the upper, middle, and lower. So there's probably some sort of baffles here that are meaning we get an early response in this middle zone, and then a response in the lower zone, and then we see the CO2 coming in an upper zone as well. Interestingly, there was a CO2 arrival that did appear later on in a shallower part, still the Mount Simon zone, but in a shallower part in the CCS 1 well. This was either due to injection in the CCS 2 well or possible movement of CO2 vertically up through formation. So initially, the model didn't very well match with what was seen in the monitoring wells. So baffles were introduced, low permeability baffle zones were introduced in the model. Now, when I say a model, this is a 3D grid, a cellular grid that is used to run plume simulation. So what was done is they went back to the original logs, tried to understand where these baffle zones could be, and they ran multiple iterations to put in the baffles to try and match where the CO2 plume was in terms of the expected entry into the monitoring well, or when it was seen by the monitoring well, so to say. And on this map, it's probably not very clear. This is CCS 1 well, then 1,029 feet away, you get the initial monitoring well. Then we have the CCS 2 well here. that was drilled later on. And then the monitoring well related to that is up there. So sorry if you can't see that well on the screen. And this isn't exactly a cross section. It's kind of zigzag through these. So we're seeing all of them on one slice. And here it's just showing how the plume prediction was done. So this is using a fluid simulation using Intersect to actually predict where the CO2 plume is going to go. So this is in 2012 after injection into the CCS1 well. This was the predicted plume in 2014. In 2016, this was a pause of injection. You can see the CO2 plume still moves, it still spreads out even after injection. And then in 2018, they started injecting into the CCS2 well. And by 2020, you get the response actually in the monitoring well, in the second monitoring well from that. So the simulated results show no CO2 arrival at CCS1 due to the CCS2 injection. But as you saw earlier, there was some response. So either our model isn't exactly matching, well, we know our model isn't perfectly matching what we see in the subsurface. Okay, so I have a few other case studies that we've worked on, maybe not as exciting because we're not actually injecting CO2 yet in many of these places. This was some work we did in Brazil. We've been actively investigating a number of basins in Brazil to try and find the best place to inject CO2. We start by doing a rapid type of screening based on a number of criteria and transforming them to chance of success maps. So we're trying to see essentially the green areas in terms of not only subsurface, but surface, so that we can quickly talk to emitters, and emitters can locate the nearest site with high potential to store, because they have a lot of ethanol production, which is medium scale, I would say, emissions, and they're looking for a cheap option to store onshore in these basins. We did something slightly more high level in Australia. This was actually combining a lot of 31 3D seismic vintages, 26,000 kilometers of seismic, and doing a seamless regional interpretation and subsurface evaluation to understand CO2 formation potential, reservoir capacity, the presence of the low permeability seals, and also leakage risk. So here we created a publicly available CO2 storage site atlas to accelerate carbon storage activity in the region, including acreage delineation and storage site identification. Another tool we have is a cloud-based digital tool. We use this to rank multiple sites in Trinidad and Tobago. We were investigating some license blocks which would be most suitable for CCS. This was using multiple criteria, selecting these criteria, weighting these criteria, and inputting based on the different site properties, and then ranking using a combination of analytical hierarchy process and also the TOPSIS method, and running sensitivity and uncertainty analysis. The benefits of this tool is we get a consistent and repeatable methodology for ranking. We can also benchmark to operational sites as well as understanding uncertainty. This is the score distribution plot. We have Illinois Basin up here scoring the highest, but then we had one of the sites, the East Coast Marine area in Trinidad, which had a very similar score distribution to its Zero Formation, which is the formation that they're injecting in Sleipner. This is an exciting project we're working on in the moment, and we'll be presenting in more detail at the upcoming EAGE Annual. It's Slovakia's first CCS project. It's a project that's advanced in getting the permitting from the Slovakian authority, and the application is ongoing for the permitting from the EU as well. So we've been working to help de-risk a reservoir that's been previously producing gas. And the interesting thing about this reservoir, it already has a very high concentration of CO2 in the gas, and it's already been permitted for gas storage with CO2 as a buffer as well. So this is an exciting project we're working on in Slovakia, and hopefully will be a foundation for future developments onshore in Eastern Europe. This is a project that the team in Malaysia did back in 2012 with Petronas. They were again investigating the feasibility of injecting and storing in a depleted gas reservoir. So they constructed a 3D model and then conducted 4D coupled geomechanical simulation to incorporate material property degradation due to acid carbonate interactions. So this allows for a quantitative assessment of the potential risks of leakage due to those chemical interactions. Now, we were also involved in the Sleipner project. This is the offshore, the biggest offshore commercial scale project in Europe. They've been injecting CO2 since 1996. And storing around 1 million tons of CO2 per year. So in this case, the CO2 is being separated from the gas produced in a deeper formation and then injected into a shallower formation from the platform. We were involved in the seismic monitoring, the 4D seismic monitoring to image essentially where that plume was going, and also try and match this with a high resolution reservoir modeling and plume simulation. Another interesting element of this project was the horizontal well design. A lot of the CCS projects in development tend to go for the vertical well for simplification. For simplification, but here it was a pretty complex well design. They also had issues that we see in a few different projects of sand influx, which limited the injectivity, but this was solved by reperforation of the injection interval and installation of a sand screen and gravel packs as well. One thing we also work on is adaptive MMV, so measurement, monitoring and verification program based on injection performance data. This was one of the projects in Canada in an onshore aquifer. And the challenge was understanding the near wellbore behavior and integrating dynamic operational data into our subsurface model. So we're really trying to calibrate, it's quite a theme, calibrate our model against the actual data that we have. And by doing this, we managed to devise an adaptive MMV program based on the expected performance of the injection wells. Now, one of our larger scale partnerships is in Saudi Arabia. It's with Saudi Aramco, ourselves and Linde. And this is a large hub scale project to actually decarbonize a huge region in Saudi Arabia. We're hoping for eventual scale up of over 40 million tons per year of CO2 storage, which would make it the single biggest project globally. Now, a couple of slides to finish, just talking about the success factors in a CCS project. So what do we actually need? We need policies and regulations to be in favor of CCS. We need a geological storage that's verified, and we need CO2 to be available. So in terms of policies and regulation, we need a permitting, a clear and efficient permitting system for CCS projects. We need to understand public acceptance. Are the public going to accept onshore storage or offshore storage? How far away from populations do we need to be? And what's the general government strategy? Are they supportive of CCS via grants and such? Also, what's the carbon pricing in the region? Is there an emissions trading scheme? Are there tax credits? How can we fund the project? Because it's essentially waste disposal. You know, we're not making money from CCS. In terms of geological storage, we've discussed this, but do we have a suitable capacity? Do we have suitable long-term injectivity? And most importantly, is that storage integrity, is it secure? Is it going to leak? And finally, the CO2 availability. So do we have cost-effective capture? Capture is one of the most expensive parts of a project. And it can be very complex when you're actually trying to combine multiple sources into a single CO2 hub in terms of the different purities of CO2 and the different elements within those impurities and combining those within a single hub. Also understanding how we can have cost-effective transport. Ideally, if we've got an emitter, we're injecting next door, you know, on their land. That's the ideal. You have an onshore emitter, and the cheapest way is just to drill a well next to them and have almost zero transport costs. But that isn't the reality. We might not have good geology. We might need to go offshore for public perception. There are many reasons why we're going to need cost-effective transport. Also, economies of scale. This is why in Europe, especially, the hub models are preferable, because if we're moving multi-million tons of CO2, it brings down the price of storage, of transport per ton. And of course, partnerships. We need to build partnerships and trust between the emitter, the transport, and the storage operator as well, because a lot of the emitters we talk to have no idea what geology even is, let alone how we can measure uncertainty in the subsurface. So I'm going to end on the slide I'm least comfortable with because I'm not an economist. But just to put it into perspective, how much does CCS cost? Because as I said, it doesn't make money. So the capture is a huge part of it. It's 70 to 80% in general of the cost, but it can hugely vary depending on the source of the CO2. The transport is generally the lowest part, but obviously this can depend. Are we transporting just a kilometre from the emitter, or are we transporting hundreds of kilometres to the offshore? Storage tends to be around 10 to 25%, although I would say this is quite US centric, where we're considering onshore storage. I would say offshore, we're probably going to be up to 5 or 10 times this amount for the storage, which then brings up that cost percentage as well. And this is just a breakdown. As I said, the capture, it very much depends on the source, whether it's a high purity, medium purity, or low purity source of CO2. High purity being chemical industry or natural gas processing. Medium being, for example, hydrogen production, steel production, and cement and petrochemicals. And low purity being things like gas combustion and aluminium as well. And I think that's me done. So happy to take any questions.